Okay, so today we're going to go over relative rate laws and general rate laws. Make sure everybody is up to date and understand what's going on. So I've just come up with a few problems to go over. If you guys have any questions, please let me know. So first question is write the relative rate expressions for the reaction N2 plus 3H2 gives us 2NH3. So remember our relative rate laws. We look at this right here, and then that can be translated into -1 over A delta big A delta T, this is rate, equals -1 over B little b delta big B delta T equals 1 over C small c delta big C over delta T equals 1 over little d delta big D over delta T. So that's how we're going to take our rates and relate them using stoichiometry for relative rates. So we've got this equation. If we want to write out our rates will be equal to the rate of disappearance of N2 and H2, rate of appearance of NH3. So for N2 it would be delta N2 divided by delta T. And this would be a negative because of the rate of disappearance. And that'll be equal to the negative of 1/3 delta H2 over delta T. 1/3 because it's got a 3 as a stoichiometric coefficient. And then that'll be equal to 1/2 in the positive because it's the rate of appearance of NH3 delta T. Take this and put this into action using actual numbers. So we still have the same general form for our relative rate expressions, but now we've got a rate of appearance of oxygen gas, and we want to know the rate of disappearance of KClO3. So the way we relate this is -1/2 delta KClO3 over delta T is equal to 1 over 3 delta O2 over delta T. We see from our problem that the rate of appearance, so this portion right here, is equal to 4.00 times 10 to the -3. So we'll put that into our equation and then solve for delta KClO3 over delta T. Okay, so that'd be equal to 1/3, 4.00 times 10 to the -2, molarity over seconds. And if we solve for this, we get a rate of disappearance equal to -2.67 times 10 to the -2 molarity over seconds. Okay, we're going to move from our relative rate expressions to our general rate expression. Anytime you see a table full of concentration and rate data, that's what we're talking about. So we've got experiments 1, 2, and 3. We vary our A and B concentrations and we get a rate out of that. So when we want to figure out what our rate equation is for this reaction, we need to figure out Mn. So we've got a color code. A is going to be, A or M is going to be pink. B or N is going to be purple. So let's start with A. So we're going to say X is equal to 0.60 divided by 0.20. I choose experiments 1 and 3 because we have A changing, B staying the same. We divide that out, we get a value of 3. For our y, we're going to take 6.3 times 10 to the negative 3 divided by 7.0 times 10 to the negative 4. When we divide this out, we get a value of 9. And then when we say x to the m is equal to y, we have 3 to the m is equal to 9, and we get an m equal to 2. So now we figured out our m value. Now we just need to figure out our n value. Same exact thing. Actually, let me do some erasing real quick. Have enough here. It's still there. So now we want to look at two experiments where our A value is not changing, but our B value is. So we're looking at 2 and 3. So our x is equal to 0.60 divided by 0.15, which gives us a value of 4. And then our y is equal to 2.8 times 10 to the negative 3 divided by 7.0 times 10 to the negative 4, giving us a value of 4. So 4 to the n is equal to 4, n is equal to 1. So we have A being second order, B being first order, and our rate law, or rate equation, is equal to K A squared B. Okay. There we go. We want to now use the information we just gained to determine our numerical value for our K, and we want to know its rate constant. So it doesn't matter what you use, what value you use, what experiment you use. I'm going to go with 1. Just any experiment, just stay consistent, so you'll use the concentrations for the experiment you choose, and the rate. So my rate is 6.3 times 10 to the negative 3. That'll be equal to my A concentration, 0.60 squared. Oh, there's my K. And my B concentration, 0.15. And I'm going to solve for K. When I do this, I get a K value. Oh, in units. We need units. When I do this, I get a K value of 1.17 times 10 to the negative 1. This is third order, so I'm going to have a unit of s to the negative 1, molarity to the negative 2. Let's move on to our next relative rate law problem. We have the hypothetical reaction as such, and we have our initial data down below. So if all the things were done at the same temperature, we want to be able to determine our rate law. So again, we're going to do our m and our n. So let's first solve for m. So I'm going to choose, so there's my y staying the same, my x changing. So I'm going to say 0.40 divided by 0.20 gives me the value of 2. And then 7.0 times 10 to the negative 4 divided by 7.0 times 10 to the negative 4 gives me a value of 1. So 2n equals 1. N is equal to 0. So we are 0 order in x. Do the same thing for our y, or our n. So look at what values we want to use in this case. Okay, here is an instance where we're keeping our X concentration the same, but changing our Y concentration. So we'll use these values. So we divide that out, we get a 4, and then we get a value of 4. So that means 4 to the n is equal to 4, so n is equal to 1. So our rate expression in this case would be rate is equal to k y. We're going to then use this data to figure out our actual k value. So again, I'll just stick with experiment number 1 and the data that's in there. So we have rate of 7.0 times 10 to the negative 4 molarity per second is equal to K times by 0.10 molar. No squares, no anything else. Our X is not in here because it is a reactant order of 0, so anything to the 0 is just going to be 1. We solve for this. We get a value of 7.0 times 10 to the negative 3, a unit of seconds to the negative 1, because we have a first order process. Now it asks, how long must the reaction proceed to produce a concentration of Z equal to 0.20 molar if the initial concentrations are as such? Okay, so we want to determine how long it will take to actually get to our product. So this is kind of a different type of thing. We're looking at this equation again. So we have 2x plus y going to Z. We have our initial concentrations, and we have a end product that we want to determine the amount of. So this is a time thing. Just bringing a little bit of extra thing in here. It's a little integrated rate law, a little bit of half-life. So I'm going to go through, and actually look at my half-life. So half-life for a first order process. 0.693. Oh, you know, I don't need to do all that. Let's not do half-life. We can just go directly into our integrated rate law for a first order process, which is ln a to the t is equal to negative kt plus ln a naught. Our a in this case is going to be our y, right? You don't care about the x concentration because it doesn't change anything, right? So we'll put these values in here and solve for t. So we want a concentration of Z to be 0.2 molar. So if we look at what point do we get 0.2 molar? We get to 0.2 molar when we've reacted 0.2 molar of our Y, right? So when Z equals 0.20 molar, our Y will be 0.60 molar minus 0.20 molar. So it'll be when Y is at a concentration of 0.40 molar. Okay. Now, we're going to then take this. This will be our AT. This will be our A0. We have our K value from above. We're going to solve for time. So this is a tricky way of doing this. So I hope you guys are paying attention because this one's a good one. Okay, so I'm going to say ln of 0.40 molar is equal to negative K, which is 7.0 times 10 to the negative 3 seconds to the negative 1, times by my time, plus ln 0.60 molar. Okay, so now I'm just going to solve for my time. ln.4 minus ln.6 divided by negative 7.0 times 10 to the negative 3 gives me a time of 57.9 seconds. That was fun. I like that one. Okay. So I know this is supposed to be relative rate law and general rate law, but I wanted, we've already gone over the integrated rate law, so I want to make sure that you guys can do more. So I'll do a separate video on all integrated rate law.